This video will continue on with the two-factor analysis of variance, and in particular we'll discuss in this video the different hypotheses. So for a two-factor analysis of variance, we have three hypotheses, one for the main effect of A, one for the main effect of B, and one for the interaction. So let's just remind ourselves that in a factorial design, we have an experiment that has more than one factor or more than one independent variable. So whether it's an experimental independent variable or quasi-experimental, it can be used in a two-factor ANOVA. So you may have something that's truly manipulated, which would be a true independent variable, or a quasi-independent variable, which is something that's naturally occurring, like males versus females, or level of anxiety on a test, and you separate it into high anxiety and low anxiety. So either types of those variables may be employed in a two-factor ANOVA. And we're going to have three tests. So each test is going to have the same basic F ratio structure. So this is what that F ratio would look like. And it looks very similar to the F ratio we saw with one-way ANOVA for independent measures. We have the variance, or the differences between treatments, in the numerator, and then we have the variance as expected with no treatment effect in the denominator. So as we said, we're going to have three hypotheses tested by these three different F ratios. So I have three hypotheses, and then in your analysis, you'll get three separate F ratios. So first are for the main effects. So these are the differences among the levels of one factor. So we have two independent variables. So for independent variable A, we're looking at those differences. For independent variable B, we're looking for differences among those levels. Those differences are tested for statistical significance, and you get an F ratio. Each factor is evaluated independently of the other factors in the study. So looking at one independent variable, regardless of the other independent variable. So for our hypothesis, we're going to see that that null hypothesis is going to say that the mean of level 1 for treatment A is going to equal the mean of level 2 for treatment A. And the null hypothesis is going to say that they aren't going to be the same, that there's going to be some difference. And then we're going to have a hypothesis for the main effect of B. And again, the null hypothesis would say that the mean for level 1 of treatment B is going to be equal to the mean of level 2 for treatment B. And the alternative hypothesis would say that they are different. The idea is that the results of one are independent of the others. And again, we get an F ratio for this main effect and an F ratio for this main effect. So here we have two distinct hypotheses with two distinct F statistics. So for the main effect, we're looking at the mean differences among the levels of one factor, one independent variable. We have, in a two-factor study, we have two main effects, one for each factor. So here in our example, and this is the same example from the previous video, we have factor A, which is group type, and we have factor B, which is social interaction. And so when we're looking at the main effect for factor A, we're looking at the mean differences among the level, regardless of what's going on in the other factor. So we don't want to compare these means because these means are dependent on this factor, factor B. These means are not dependent. They're the overall means. Regardless of what's happening in the other factor, do we have a significant difference? So for factor A, we're comparing the column means, the overall means. For factor B, and so that's the main effect of factor A. For factor B, again, we don't want to compare these means because these means are dependent on group type. Independent of the other factor, is there a significant difference in factor B? So that's the main effect of factor B, where we would consider and compare the row means. So we want to see for factor B, if these row means are significantly different, we get an F ratio. And that will tell us if there's a significant difference. We would compare these overall means and get an F ratio to tell us if these are significantly different. And then, so that was 2 of the 3 hypotheses. Then we also have a hypothesis for interactions. So the interaction says that the mean differences are different than what would be predicted from the overall mean effects. In other words, the effect of one factor depends on the different levels of a second factor. So that they're not additive. The main effects do not add together. There's some sort of dependency upon them. So our hypothesis would be, for the null hypothesis, that there is no interaction between factors A and B. And the alternative would say that there is an interaction between A and B. And you can't state all of the different potential interactions, so that's why it's just there is an interaction. So back to our example, now we're considering these mean differences. These differences were for the main effects. Now we're interested in what's going on. Does differences in one group depend on the other factor? Does differences in one factor depend on the other factor? The idea with an interaction is one factor has a direct influence on the effect of the second factor. Or another way of wording it, the effects of one factor depend on the levels of a second factor. And the interaction is represented as A by B. So independent factors have no interactions. So when you have independent factors, you just have main effects. Dependent factors have interactions. So that's where you say the effect of one factor depends on the other factor. This is just a little mean. Ran a two-way Anova and found an interaction effect. So it's exciting when you're doing a statistical analysis and you find an interaction. Wow, now you've really got something to talk about. Of course, you don't typically do a factorial design unless you suspect there's going to be an interaction. All right, so now for just another example to hopefully help you understand what an interaction is. So I have 2 bottles filled with different chemicals. I have a flask here with hydrochloric acid, and hydrochloric acid is highly caustic, dangerous. It will dissolve many materials, including metal, wood, plastics, and flesh. And then I have sodium hydroxide. Sodium hydroxide is also highly caustic. It will dissolve hair, fats, and flesh, which makes it's a common ingredient in drain cleaners. So I'm going to ask you a question. I have 3 shot glasses. So and think of it as I have these 2 substances, that's one factor, and then I have concentration as a second factor. For $1 million, would you drink a shot glass of hydrochloric acid? For $1 million, would you drink a shot glass of NaOH? And it probably, for hydrochloric acid, it depends on the concentration, right? For sodium hydroxide, perhaps it depends on the concentration. And your answer for this is independent of your answer for this. Now, would you drink a shot glass containing both sodium hydroxide and hydrochloric acid? Now, substance A, hydrochloric acid, is caustic, and substance B, sodium hydroxide, is caustic. Then adding the 2 together should be doubly caustic. That would mean that we would have no interaction, that the effects of factor A and factor B are additive. So again, for $1 million, would you drink a shot glass, a double shot glass, because we have a shot of HCl and a shot of NaOH? Now, if you said yes to either one, what about this one? Well, what if I told you that the effects of these 2 were not additive? That the effect of one depended on the effect of the other. So the interaction of NaOH and HCl produces salty water, NaCl and H2O. So if you had equal amounts in each, you would just get salty water. Now, it might make you feel sick. Double salty water might not taste very good, but it wouldn't harm you like a shot of HCl or a shot of NaOH. So the interactions are different than what would be predicted by simply adding together the individual main effects. So for an interaction, the effects are not additive. The effects of one depend on the effect of another. Again, one factor has a direct influence on the effect of the second, The effects of one factor depend on the levels of a second factor.